All right, hello everyone. My name is Andrew Akins. I'll be covering for Group 1, the refrigeration cycle experiment. I'll be a reporter for this. So a little outline of what we're going to be going over. First, I'm going to be going over the overview and theory behind the refrigeration cycle. We'll be going over the apparatus that was actually used in the experiment, as well as the experiment and procedure that was covered by the group leader a while ago, as well as the results I recovered from doing this experiment. Also some uncertainties that could be associated with doing this experiment, whether that be the values, any values in calculator and machine itself, as well as some conclusions that I made and any questions. So why study the vapor compression cycle? So we want to know how we can remove heat from a cold source and put it into a hotter source. Now, second law of thermodynamics states that we need to input work into the system in order to be able to do this. And we're just going to be investigating to figure out how we're going to be able to do this. So some theory and key concepts. So for the ideal case, for states 1 to 2, we're going to assume isentropic. And then for states 2 to 3, it's going to be isobaric, which means P2 is going to be equal to P3 over the condenser. And then from states 3 to 4, it's going to be adiabatic, which means the enthalpies are going to be the same over the thermostatic expansion valve. And from states 4 to 1, it's going to be isobaric, meaning that P4 is going to be equal to P1 over the evaporator. So a little bit about the thermostatic expansion valve. What it does is it controls the amount of refrigerant that's able to flow across a system. It also takes a high pressure and relatively high temperature fluid and rapidly expands it to become a low pressure with relatively low temperature fluid. And it also changes the refrigerant state from a saturated liquid to a saturated vapor liquid mix. So as I said before, this is an adiabatic process. We're going to set Q is equal to 0, as well as set it equal to the change in internal energy plus the work done. And so by doing this, we can derive through the equation, and we get to this point where U4 plus P4 V4 is equal to U3 plus P3 V3. Now, from thermodynamics, we can conclude that this is equal to enthalpy. Therefore, we can set the two enthalpies equal to each other. Hence, it is adiabatic. So I'm going to quickly go over the experimental procedure. For exercise 1, we had to do it 5 liters per minute, which we took the values of the hot temperature of the water and the cold temperature of the water, as well as the work input to the compressor. For exercise 2, we set it to 6 liters per minute and 40%, the compressor at 40%. And we took the values for pressure and temperature at all 4 states across the refrigerant. We repeated this for flow rates of 3 and 4.5 liters per minute. So this is an overview of the system that was used. ST2 and SP2 are the inlet to the compressor. SP1, ST1 are the outlet to the compressor and input to the condenser. ST3 is the temperature output of the condenser, and ST4 is the temperature outlet of the thermostatic expansion valve, and it's the input to the evaporator. And this is just an image of the software used that was sent to us during the break. And so some important equations used: the heat rejected of the system. We can take the mass flow of the water and the specific heat of the water and multiply it by the temperature change over the condenser to find the heat rejected out of the system. We also have electric power consumed, which can be defined as the enthalpy change across the compressor, and this will be the work input. So important equation really is the coefficient of performance. And the coefficient of performance, the real equation, or the actual value, is the heat rejected over the work input, which can also be defined as the change in enthalpy over the condenser divided by the change in enthalpy over the compressor. And then the coefficient of performance, the ideal situation, will have the temperature of the cold reservoir divided by the temperature of the hot reservoir minus the temperature of the cold reservoir. So a little review of the refrigeration cycle, a pressure versus enthalpy graph. We will have the work input here of the compressor. In the ideal situation, we're going to have constant entropy, but this isn't going to be the case. So we're going to have a slightly higher enthalpy in the actual version. And then we're going to have the enthalpy change across the condenser. And it's going to get to a saturated liquid here. And then across the thermostatic expansion valve, we're going to have that change to a liquid vapor mix. And then we're going to have the heat rejected from the heat input from the cold reservoir across the evaporator. So from exercise 1, these are the obtained values that we got. And from this, we can calculate the Qgen, which is about 1.3892, which is heat rejected into the hot reservoir. And these are our coefficient of performance values obtained. As we can see, the ideal is higher than the actual, which means it satisfies the second law of thermodynamics. So this is the results that I got from the first case. And as you can see, we have on state 1, we have a slightly higher enthalpy than the ideal situation. That's going to be in the superheat range, as well as state 2. So that's just going to show you that there's a slightly higher enthalpy at state 1 instead of just being directly on the saturated vapor line. Same for 4 liters per minute and for 3 liters per minute. So some uncertainties that we could have encountered in this experiment. I could have made some errors in the whether or not being interpolating the enthalpy values or just some calculations in general. Any errors in operating the machinery. From what I read, we were sent 4 liters per minute instead of 4.5 liters per minute, so it won't be a 4.5 liter measurement necessarily. And any errors in the sensors itself within the machine. Some conclusions that were made is that the change in enthalpy from states 2 to 3 will be lower in the ideal case due to less work needed for the input in the compressor, and the more work will be needed to be input in the actual case in the compressor. And the actual case, the actual coefficient of performance will be lower than the ideal coefficient of performance. And these are my references, and thank you.